Hello physics, here we are to talk about section 4 of chapter 17, and it's talking about power, electric power, and we're going to have to talk about the types of current there is. There's direct current and alternating current. So let's start with the most fundamental basic concepts of current, and that is direct current. Direct current is the kind of electricity we get from batteries. And here's the concept. Let's say that we have a magnet and we have a wire. Wires have, or conductors have electrons that can move. The thing is, how do you get them to move? Well, you might remember from our experiment that we talked about with discovering the electron, the cathode ray tube was unique in that you could take a magnet to it and it would bend the beam. So electrons were affected by a magnetic field, and they are even though they are in a wire. So what we can do is we can take a magnet and we can run it down past the wire and make it conduct electricity. The trouble is it has to have a circuit because I can't just push electrons this way. They have to have a place to go. It's kind of like water in a pipe. I can't just squeeze it and make it go somewhere. I have to have the water has to have somewhere to go. So usually we have to have a circuit. So I'm going to connect these wires so that there is a circuit. But you'll see that if I run the magnet here, that needle doesn't really move. And I am creating electricity. It's just such a small amount that it's practically not measurable. So what I've got hooked up here is a bunch of coils of wire. So the wire has gone here and coiled hundreds of times around, trying to make it so that this magnet gets to influence its push on the electrons over a wide range. Again, if you see me go like this, the needle doesn't hardly move. But if I put it in here and I shake it back and forth, you can see that that needle moves. And I'm actually making electricity by moving this magnet back and forth past this wire, pushing the electrons. Now, if I could push it only one way, I would make the electrons go one way. But then when I shake it and I push it the other way, the electrons go the other way. Now, when they're only going one direction, we call that direct current. It goes one way. If I make my magnet go back and forth, it's alternating between one way and the other way. One way and then the other way. Back and forth, and now I'm making alternating current. Well, both types of current have their advantages and disadvantages and reasons for them. A battery is our source for direct current because it's a chemical reaction that produces electrons, and it's kind of like a lake above the ocean. There's energy in the lake that can flow down to the ocean, and it only goes one direction. We don't have the water going both ways. The unique thing about electrons is we can push them back and forth, and that's what we were just doing here. So batteries only can supply direct current, whereas that's maybe not always so convenient. Like if I'm trying to make electricity, it would be very annoying to have to push the magnet through and then to come back and push it through again. I would not be able to produce very good electricity. But if I could make it so I could go back and forth over and over and over again, I could create electric current. It just would alternate. And we can do this with things called motors, where we can take water going through a dam and make it spin and make the magnets go around and around and push these electrons back and forth in alternating current. It also travels much farther. That's one reason why all the electricity in houses and schools and so forth, that's all alternating current. It's created by generators, by this, it's not back and forth, but a round and round motion, and that creates the alternating current. Now, back to the idea about magnets and electricity, just to illustrate that we can create some electricity with a magnet, or make a magnet using electricity. Take in a nail, and I'm going to reverse this process. We've wound a wire around this nail, and we're going to run electricity through it and see if we can make it into a magnet. So I've got some paper clips here, and you can see that it does not pick up the paper clips. But if I hook it up to a battery, lost my battery. Oh, here it is. I can hook it up to the battery, and when I run electricity through it, you can't see it, but you can see the results. You can see that it picks up the paper clips. If I disconnect it, it falls off. So there it is as a magnet. Now, why put it around a nail? Well, if I take the nail out, the magnetic field is still there when I put it through electricity. It just, the iron sort of focuses it. See, I can't really do anything. There's still electric field, magnetic field there, but it's so little it can't pick up anything. So it turns out that when we put an iron core, that iron, which can be magnetic, magnifies the field from the magnetism created by the coil, and it makes it so that we can pick up things. If I can get these guys to stay on. Okay, so magnets can create electricity, and electricity can create magnets. They go together. So let's take a look here at this apparatus here. This is a bell, typical bell you might have in a school or something like this. And here we've got two coils of wire, kind of like this. When we run electricity through that wire, it creates a magnetic field and it creates an attraction. And so we're going to run electricity through these things. It's going to attract and pull this metal here, which is going to pull it towards the bell and make it ding. Now, we don't want it to just ding once. We want it to ding lots of times. So how do we get it to go back and forth? Well, run the electricity through here. It attracts it, and then there's a little connection here that allows electricity to go through. When it pulls this way, it disconnects right there, so the electricity can't go through. Well, if it can't go through, what happens to the magnetic field? It goes away. No more attraction, and the little lever goes back to where it was. When it goes back to where it was, it connects the electric current, so electricity can go back through these coils, create a magnetic field, and attract it again. So it attracts it again. Oh, I'm attracted again. And it goes forward, which disconnects it here. So electricity doesn't go and shuts off the magnetic field, which no longer attracts and lets it go back. And so it goes back and forth and back and forth. So let's see if this works. Okay, I'm going to try to bring this close to the camera so you can see the little spark that's going on inside of the... So as the video progresses, I'm trying to show you the spark that occurs inside between the electromagnets and the little rocker arm or hammer that dings the bell. So here comes reduced sound, but look for the little spark going on there, kind of in the middle, upper left, and then up comes here now a slow motion, so you can watch it and look for the spark as it turns on and off. Electricity has resistance. When it goes through wires and so forth, it's kind of like friction. As the electrons bounce around, they hit things, and that creates heat. Well, some things don't create much heat. We call those very good conductors, like copper, silver, and gold. Other things create a little more heat, like iron and tungsten and so forth. So we can choose our materials to do what we want them to do. So in these wires, we've chosen copper because it's a very good conductor. But in a light bulb, we can choose... In a light bulb, we can choose to put for a little short distance something that has very high resistance, creates a lot of energy, in this case creates light. So we can take a cord that has very low resistance, connect it to a little bit of wire that has a lot of resistance, and create some light. Now, when it comes to vacuum cleaners and motors and things like this, how can we get jobs done without having to have magnets in them? Well, I want to show you a little bit more about generating. I showed you how to move a magnet past this coil here and produce electricity. So here I've got a really pretty strong magnet. So you can see the compasses there getting messed up by the magnet. Well, I'm going to run it past here. Watch the needle. See, even from outside the coil, I can get it to move and produce electrons. Because I'm going back and forth, it's what kind of electricity? Alternating current. Now, what if, could I use electricity to create the magnet to create more electricity or to create a motor? And so what we can do is we're going to put this coil in here and connect it to a battery to see if I can generate electricity by creating an electromagnet. And, well, I didn't get very much just connecting it this way. What if I put a metal rod in here, just like the nail has iron in it and is in this coil? I'm going to put a rod inside this coil, inside the other coil, and let's see what happens. Okay, so watch the needle. You can see here with the iron rod in here, I'm actually changing the magnetic field, and I can generate electricity. Again, since it's going back and forth, that is alternating current. Now this is a chunk of iron, which you can see by the fact that it sticks to this magnet. This one is not iron. It won't stick to the magnet. What happens if I put that in here? And you can see, not much. We need that iron to let go of the magnet, and then we can use it to generate electricity. So you might remember our friend, the Lego motor with the capacitor that we used when we did our Lego projects. I've hooked this up to the wires and then to this light bulb, and this has magnets in it, and when I turn it past the magnets, I can generate electricity. If I could keep it going, then I would generate direct current. If I go back and forth, I would be generating alternating current because I make it go one way and then make it go the other way. And that's how a generator works. Running copper wire past a magnet. Oh, I came disconnected. It's very hard to turn when it's connected to a load. And when I disconnect it, it's very easy. In fact, it just keeps on spinning because it's not having to do any work. So let's continue our look here at section 4 of chapter 17, page 606, and electric power. First of all, we talked and demonstrated the idea that there is two types of current. There's what we call direct current. This is the first electricity that most people discovered and understood. It comes from a battery. And it's because chemical reaction produces electrons and it just keeps on flowing just like water out of a lake. Whereas alternating current is where the electrons go back and forth, and that's usually caused by a battery, by a magnet going back and forth along a wire. Now when you look at a graph of these two kinds of current, if you look at this graph, here's time, here's how much current, and this would be 0, so it's above 0. And this current is basically constant until, kind of like a lake running out of water, the battery runs out of electrons and eventually drops off to 0. Alternating current is never constant, it just is constantly changing actually. And so the electricity, or I should say the current, goes towards lots of it is flowing, down to 0 and flowing, then lots of it going the other way, and then, so it's coming from back and forth, back and forth. And if you were to graph that, there's a moment at which it's, a lot of it is going past, and then it comes to a stop, and it comes back the other way, and a lot of it's going, but it's going the opposite way until it comes this way and stops and goes back and forth. And so if you graph that, that's what alternating current goes like. This is one reason why you might hear when things are operating, like lights up in the ceiling or a TV set or something like this, you might hear this hum, or sound systems in auditoriums and churches, you might hear this hum. And that's from this alternating current that's created by our house electricity is 60 cycles per second. Now, each electricity can be converted from one to the other. When you plug in your cell phone charger, you're taking alternating current, and that little box on the end is converting it into direct current. And that's what's charging your cell phone, because your cell phone works on a battery. So we have to take this kind of electricity and turn it into this kind of electricity. And we can go the other way. We can actually take battery electricity and turn it into alternating current. They can be turned back and forth by what we call transformers. Big or small, like up on the telephone poles, those big gray things, those are transformers, converting a kind of electricity. In that case, it's stepping it down from the voltage, very high voltage, to a lower voltage. Now, on our next page, we can see our equation. We're looking at how much power we get. You might remember from a long time ago that power equals work divided by time. Well, in electricity, what is the way that we measure work? That's the change in potential energy over time. That's also work, but in change in electrical potential energy is the change over the charge. And so we can take and substitute that in for the equation for power, and we get power equals the current times the change in voltage. So got interrupted there. We were looking at the equation of power and Q delta V, since P equals Q delta V over time. And since back here we learned that current equals Q over time, and since over here we can have Q over time, then Q over time becomes I, and we get power equals IV, current times the change in voltage. The SI unit for power is the watt. That's one reason why you're familiar with seeing that, especially in light bulbs, but it measures everything, and in fact electricity is sold in kilowatts. And there are more substitutions and equations that you can use depending on what the given information is. So here is the next assignment, given information, and the answers as well. On the next page, it actually deals with something very practical. That is, how much does electricity cost? And it shows you calculations here for, you usually get charged for every kilowatt hour. That's the amount of kilowatts used in 1 hour, or 1 kilowatt used over an hour. And so that's how that's calculated. There's one question here, and the answer is right here, $0.13 or 13 cents. Okay, so that's it for this section. There's one more cool little demo to show you. And when we run a magnet through a pipe, that magnetic field induces the electrons to go around in a circle. Well, as they go around in a circle, they create a magnetic field, which happens to be opposite of the field of the magnet that's going through it. So while it tries to fall, the faster it falls, the more electrons move, which means more electromagnetic force, which opposes it and slows it down. So when it slows down, it creates less current with less resistance, so it can speed up. So it gets to a point where it can't go any faster. So to illustrate how this goes slower, it's a little bit hard to tell, but I'm going to drop this magnet through here and then this one right next to it, and see if you can see at the bottom which one comes out first. All right, 3, 2, 1. So you can see that the one through the tube took longer because it was being slowed down by the magnetic field. 3, 2, 1. I think that's really cool. This is a slow motion of the magnets falling, and you can hear it starting in just a second here. even though you don't know when I release them. Here's one more little slow-mo, and you can use your ears to know when I actually release both at the same time as they start to fall.